Hello, welcome again. We are covering the subject Steam Engineering for Civil Services Mains, IFS and various GATE exam. Next topic in the chapter of analysis of steam cycle is your regeneration. So now we'll study the concept only, concept of regeneration, why regeneration is needed. So here first we analyze this external irreversibility in the Rankine cycle. So here this is your water, and this water is in economizer and it is heated by this gas, and the temperature difference here is very large. Okay, so which is causing irreversibility. So if this water is being heated by this steam, we extract some steam and heat this water from 4 to 5, then this external irreversibility which is due to the temperature difference can be reduced or completely eliminated if we are able to heat the water from 4 to 5. Okay. So if we are able to uh, reduce or eliminate this irreversibility, then mean temperature of heat addition would be determined by this part. Okay. So mean temperature of heat addition will increase, which means the efficiency will increase. Okay. So that is the concept of regeneration. Okay. So I will read out this. The mean temperature of heat addition can also be increased by reducing the amount of heat added at low temperature in liquid phase in the economizer section of the steam generator. So economizer section of the steam generator is your this part, heating of water. Okay. So if we are able to reduce this about this heat, then we will be able to increase the mean temperature of heat addition. The irreversibility in this section could be entirely eliminated if the feed water could be entered into the steam generator at saturated liquid state rather than the liquid well below the saturation temperature. If we are able to heat this water up to that point, then the water entering the boiler would be at higher temperature and at saturation temperature. So then this irreversibility can be eliminated. Next point is, this is possible by process of regeneration in which energy is exchanged internally between the expanding fluid in the turbine and the compressed fluid before heat addition. So if we are able to exchange this heat from steam to this water, then they are all almost at same temperature. Okay. So then this irreversibility can be reduced. Now this concept is more uh, visible in Stirling cycles. In Stirling cycles there are two constant temperature heat addition two isothermal processes and two constant volume processes. 4-1 is your constant temperature heat addition and 2-3 is your constant temperature heat rejection. This is your expansion process and this is your compression process. So in expansion process, this is your expansion process. In expansion process, heat is being rejected, and in compression process the heat is being supplied. Okay, so if this heat rejection is used in this part, if this heat rejection is used in this, heat supplying this part, then this would be a regeneration, and then the efficiency of the Carnot cycle, or the efficiency of the Rankine cycle would be your efficiency of Carnot cycle. Okay, so this is the basic concept in regeneration. So I'll read out a well-known gas cycle that uses regeneration is the Stirling cycle, comprising two reversible isothermal and two reversible isothermal constant volume as shown in here. Okay. So this is your isothermal, this is isothermal, and these are constant volume. heat addition at constant temperature T1 from an external source and heat rejection at constant temperature T2 from an external sink take place in process 4.1 and 2.3 respectively. Regeneration or heat exchange occurs reversibly between two constant volume processes 1, 2 and 3, 4. Between this 1, 2 and 3, 4, here heat is being rejected and this heat rejection is heating this 3, 4 is used here. Okay. So the area under 1, 2 and 3, 4 denoting the heat lost by the expanding fluid and gained by the compressed fluid are equal. So if we take this area under this line, that will give the heat rejection, and if we take this area, then it will get heat addition. So this heat rejection is used in supplying heat here. Okay. Therefore, all the heat is added reversibly at T1 and all the heat is rejected reversibly at T2. So ideal Stirling cycle would have the same efficiency as a Carnot cycle. So here, if we are able to supply this heat rejected to this process, then there will be only two processes left in which heat exchange takes place. That is 4.1 and here 3.2. Okay. So then the efficiency will be a Carnot cycle efficiency. Okay. So this is the ideal process for or ideal cycle for regeneration. Okay. So now we'll use this concept in steam power plant or in Rankine cycle in the next video.